Hi, I'm Anandan, Managing Director of Microsoft Research India. Let me present a demo called Stratus, Cloud Support for Efficient Mobile Communication. This will be presented by Dr. Vishnu Navda, who is a member of our Mobility, Networks and Systems Research Group. This group works on topics such as mobile computing, network systems, and cloud computing.
Hi, I'm Vishnu Navda, a researcher in the Mobility Network Systems Group at Microsoft Research India. Today I'll be demonstrating a technology that we developed here called Stratus. So at a high level, Stratus is basically designed to deliver smart, energy-efficient connectivity to mobile devices, such as smartphones and tablets, by leveraging resources in the cloud. So before I begin talking about Stratus, let me just give a brief description about the problem setting. So here I have energy characteristics of a mobile device which is equipped with a 3G cellular interface. So I have a plot of power consumed over time, and in this particular experiment, the mobile device started communicating for a short period of time at the beginning of the experiment. And if you notice, in the start, when the device was idle, the power consumed was as low as 200 milliwatts. Now, as I start communicating, the radio interface turns on and goes to a high power active state, and the power consumption is almost 1100 milliwatts. So this is almost 5 times as high as the base energy consumption. The second problem that you see is the communication overhead. So these interfaces don't turn on and turn off instantaneously. Notice that even after the communication ended, the radio remains in a high power active state for a long duration of time. So this is the communication overhead for every communication that you do. Now, for example, if you have an application which is doing sporadic communications, the radio will remain in a high power active state for a long time, thus draining energy. The third problem that we find out is the impact of signal strength. So it turns out that if you're operating in a poor signal condition, the energy consumption is much higher. I have a plot of energy per bit for various signal strength values. The leftmost bar corresponds to poor signal conditions, and the rightmost corresponds to good signal conditions. And you can notice that the energy difference is as high as 7x. So given these insights about energy consumption of a cellular interface, we went on to design Stratus. The key idea is to sort of shape your network traffic in order to match it better with the energy characteristics of a cellular interface. In Stratus, we leverage a proxy in the network which is acting as an intermediary between the phone and the internet. All traffic that is being sent and received by the phone is mediated by this proxy. Now, we employ several optimizations on the link between the proxy and the phone, wherein we get all the energy savings as well as byte savings. So let me talk about these optimizations. So we employ compression in order to reduce the number of bytes transferred on this link. As a result, we are able to reduce the time the radio is going to be active and doing communication. As a result, we sort of address the problem 1. Now, the decompression on the phone is designed to be very efficient so that bandwidth saving translates to energy savings. The second optimization we have is aggregation. The key idea here is to sort of batch together sporadic communication and send it in one shot. As a result, we sort of save on the second problem, which is the energy overhead for each communication, right? So by batching together, you sort of pay far fewer communication overheads. The third problem is basically about the signal strength. So what we employ here is an optimal scheduling strategy which looks at signal strengths. So the key idea is we sort of look at signal profiles for your frequent routes, how the signal varies over your, say, home to office route. And the next time a user goes along the same route, we use the profile to predict when the signal is going to be good and schedule in those periods and get energy savings. Now let me show you a demonstration of these optimizations on the phone. So this phone has a client which basically connects to the proxy in our Azure deployment. Now, what I have here is I'll basically go about showing you a browsing session and show you how much energy and compression savings we get. So for example, let me open a browser session. So I'm just going to a certain page. This is a very light page. And you can see that the IP address here is basically an IP address of a cloud hosting. Let me do a few more sites here. So I'm loading a page here. And what's happening here underneath is the requests are being sent all the way to the proxy in the cloud. And the proxy basically does two things, compression and aggregation, and sends back the results to the phone, and the phone is basically loading the page. Right? Now let's just see how much savings we got for this simple session here. The total bytes that were actually received by the phone, the decompressed size is 900. But we already saved around 480 kilobytes in this simple session, and the compression is like 53% here. If I do a few more apps, you'll notice the same thing. And apps requests are being basically sent to our proxy. So it's just loading the data. So now the bytes transferred is increased, and we still are seeing quite high compression savings here. How about the energy consumption? So let me quickly go over to another monitor here, which shows the energy savings for this transaction. So what I have here is power measurement of the phone. So notice that as soon as I start loading the page, the power consumption increases. And once the radio is done with communication, it should go down. So the scenario one is showing you energy consumption when you're going directly to the site and not using Stratus. Now, the total time to load the page was 25 seconds, and the energy consumption was 2000 microampere hours. Now, if I were to do this with Stratus, notice that it loads much faster, so the radio on time is much shorter. And in terms of energy, we just take half the time to load the page, and we consume half the energy. Now, let me go to the second demo, which is basically signal-aware scheduling. So what we have is an actual drive where we had a phone which was playing audio stream, something like a Pandora audio stream. And I'm basically showing at real time what is happening during the drive. Now, on the rightmost bottom part is the actual location of the car. Top is basically a front view camera of the drive. Right here, I'm showing the instantaneous signal qualities. There are two curves here. One corresponds to the actual signal strength, and the second curve corresponds to the predicted signal strength. And I'm also showing the playout buffer state, which is basically how much data have I already received from the network, right? Now, notice that I'm comparing two things here. One is a naive approach where I'm just going directly and fetching irrespective of the signal quality. And the second one is if I were to download only chunks of data at the right times. So the green bars here corresponds to the periods of time where I download data. And these corresponds to periods where the signal is good. And notice that the energy consumption is much lower compared to a naive approach, which just downloads irrespective of how the signal quality varies. Another constraint we take into account is the state of the playout buffer. I should make sure that there are no disruptions when I'm listening to the radio stream. And that's all I have with this demonstration.